This is a presentation on septic systems prepared for advanced water quality engineering. In the US, about 25% of our residents rely on individual septic systems or small community cluster septic systems for their sewage treatment. In Connecticut, it's roughly about 30% of our residents who rely on these systems. In a year, on average, about 10 to 20% of these systems malfunction due to lack of maintenance. A septic system is an on-site subsurface sewage disposal system that removes sewage and drains the water, and they're designed to protect public health and the environment. They consist of four main components: the building sewer, which is plumbing that basically connects the house to the tank. You have the septic tank itself, which settles solids and provides initial treatment by bacteria. Then you have the distribution piping, which brings the effluent to the leaching system. And then you have the leaching system, which leaches the effluent into the surrounding soil. Those components are pictured here. And this is what they would look like in real life. At the bottom of the screen, you can see the leaching system is filled in with gravel or stone material to improve drainage. The tank itself is a watertight receptacle that retains the water so that the solids can settle, essentially primary treatment. These tanks are designed to prevent floating scum and grease from passing to the leach field. The standard minimum capacity is 1,000 gallons. They're constructed of concrete, steel, or plastic, and newer ones have an inlet and outlet baffle, an interior compartment wall, and an effluent filter, which you can see here. The leaching field, when functioning properly, should not allow effluent to penetrate the surface of the ground. It should also prevent effluent from backing up into the tank or building. The bottom must be located at a minimum 18 inches above the seasonal high water table. Important factors are soil permeability, the slope of the land, and length of the system. They should be designed to ensure the volume of sewage effluent discharge does not overload the capacity. They are regulated by two different agencies. A septic system with flows of 5,000 gallons per day or less lies at the state and local health departments. These are regulated under the Public Health Code, section 19-13-B103, and they have associated technical standards. A large-scale system with flows over 5,000 gallons per day, an alternative treatment system or a community septic system is regulated and permitted by the DEEP under section 22A-430B of the Connecticut General Statutes. The design flow of these tanks has to be 150 gallons per day per bedroom, except beyond 4 bedrooms, which is then 75 gallons per day per bedroom. The minimum size of the tank has to be 1,000 gallons for all new buildings. And then in regard to the volume, there needs to be an additional 250 gallons for each potential bedroom over 3. Therefore, a household with 4 bedrooms would be a 1,250 gallon tank. Old tanks that do not meet these requirements do not need to be replaced unless there's failure or damage. However, these smaller tanks will need to be pumped out more frequently. For a non-residential tank that has less than 5,000 gallons, but is still under the Department of Health's jurisdiction, has to be designed on a basis of an estimated 24-hour sewage flow with a factor of safety of 1.5 to 2. Also, the peak flow needs to be considered. There are technical standards published in the Department of Public Health documents that have tables for schools, commercial buildings, restaurants, and other things. Technical standards also have specifications on construction materials like sewer pipes, tanks, and leaching fields. Here's an example of the table from the Department of Public Health's technical standards. If you were an engineer tasked with designing a septic system for a high school, you would look at this table and see that the design flow needs to be 12 gallons per day per student. In order order to receive a permit for these septic systems, you need to meet several guidelines. Some of them being that you are not allowed to discharge effluent to a water course, you need to have suitable soil, and they need to be above the water table by 18 inches. In addition, they need to be approved by agents of the local director of health and or a professional engineer with qualifications to investigate, inspect, and approve these septic systems. You need to file an application that is based on a site investigation, and then you need to submit a plan to the Department of Public Health or the DEEP. Once you have approval to construct, you could begin the project, but before you fill in the tank excavation, you need to have it inspected so that you can receive your permit. There are some minimal requirements when constructing and designing these tanks. They need to be 50 feet from any open water source and 100 feet from any public supply reservoir, unless specifically designed to prevent contamination. These structures that may contain sewage or septic exposed to the atmosphere need to be located at least 150 feet from any school, residential building, or institution, and they need to be fenced or made inaccessible to the public. There are minimum separation distances for any discharge that would be near a drinking water well or spring. There are also minimum separation distances for any sewer that it would be located near a drinking water well or spring. There are several other minimal requirements that are outlined in this table from the Department of Public Health's documents. For example, item 3, listed as C in the table, building served needs to be 15 feet. The septic tank needs to be 15 feet from the building. A site investigation has to be done before these systems can be permitted, designed, and constructed. You need to do a deep test pit, which is digging a deep hole within and downgrade of the proposed leaching area so that you can observe the soil characteristics, the max groundwater level, and the ledge rock conditions. You also need a professional engineer or local health department sanitarian present. You would also need to complete a percolation test, which is used to estimate the general permeability of the soil. You measure the time a water column in a small hole drops an inch. The quicker the water permeates into the soil, the more permeable it is and the smaller the leaching field. If you find your permeable rate to be faster than 60 inches per minute, then this is a very suitable condition. But you also need to be in an area that has 24 or more inches of naturally occurring soil over the ledge rock. If the area does not have this, then where there is shallow areas, you could use good quality fill, but you would have to add to 4 feet. You need to also make sure that the seasonal high groundwater level would not flood this area, and that there's 18 inches of unsaturated soil present even in the wettest period. Then you can calculate the length of the leaching field from the minimum leaching system spread factor tables or by a formal hydraulic analysis. The greater the depth of unsaturated soil and the greater the slope of the land with a faster percolation rate, meaning you could design a smaller leaching system. It's also important to consider water use. In 1992, the government passed the Energy Policy and Conservation Act, in part to promote the conservation and the efficient use of energy and water. It established national water conservation standards. For example, shower heads cannot have a flow greater than 2.5 gallons per minute. There are also standards established for toilets, faucets, and urinals. And a survey of 67 apartment buildings in New York City retrofitted with these water-saving fixtures. On average, there was a reduction of 29% of water use observed. The sources used for this presentation come from the Department of Public Health's website, the DEEP's website, as well as the EPA's.